Hey there everyone, welcome back to my channel. So we have seen the boom of pre-trained models like Chatgpt 3.5, GPT-4, which have actually turned out to be very useful. Then we saw the boom of reasoning models like OpenAI O1, OpenAI O3, Gemini 2.5 Pro, DeepSeek R1, which are according to the benchmark PhD level models. But the question is, what's next? What can be the next paradigm? So there are a lot of ideas that are thrown here and there, one of them being self-adapting language models that adapt and train all by themselves to improve their performance. This kind of behavior is actually important if you want singularity and artificial super intelligence. So is that possible? That is what we'll be seeing in this paper. As you can see, the paper correctly questions, can an LLM self-adapt by transforming or generating its own training data and learning procedure? Is that possible? Well, the answer is yes. But how does that happen? Let's have a look at it. But before that, if you're new to the channel and like more content like these, please do hit the like button and subscribe to my channel. Let's actually start with an example which is mentioned right in this paper as I've highlighted. Think yourself as a student who is preparing for their final exam of a machine learning class or any class for that matter. What do? First you read the whole book and after that you take notes to prepare for that exam. So it could be that you have read the book many months before and prepared the notes, and right before the exam you revise your notes. As it is mentioned here, the notes are derived from the lecture content, textbooks or information that is available on the internet. So you will read all of this and prepare your notes, and right before the exam you might revise your notes for the examination instead of going through the whole raw content. So this form of rewriting actually improves the ability of understanding the content, and this is what we all do. But this kind of behavior, taking notes, is not just restricted to our example of taking an exam, but it seems to be universally true for humans across various tasks. Many people do journaling and various things like that. So this is how we humans process the data. This process of taking notes and revising them is very different from how large language models typically are trained and deployed. This is now how they work, at least currently. Whenever they are given a new task, the LLMs consume the whole data as is, using fine-tuning or in-context learning, which means right within the chat. So to change this behavior, the authors of this paper are proposing a method to equip LLMs with the ability to generate their own training data or fine-tuning directives. They are calling these so-called notes as self-edits. So basically they are trying to come up with a model which actually takes notes, refers to them and learns from them, and slowly and gradually adapting and improving its performance. They called such models as self-adapting LLMs, or SEAL for short. You can have a look at this diagram to get a raw understanding. Don't worry, we'll be diving deeper into what it actually means and what the authors are trying to convey. So whenever you see LM theta t in this paper, assume that as a language model. It is written LM, language model theta t. So you can see this model is given a context, which is written as CTX, which means context. It is given some context, and based on this context, it derives 3 different learnings. It has understood something from it and it has come up with 3 different notes, if you can say. Now in this whole process, you can see these self-edits or notes are applied to the model and we come up with 3 different models. You can see the symbols. All 3 are different. So these 3 are completely different learnings, so we come up with completely different models. So now when these new models are tested, we see that 2 of them get it right and 1 of them gets it wrong. So the one which got it wrong, it means that whatever notes it took or instructions it understood, that was wrong. So this kind of behavior is penalized or discarded, and the other 2, the one on the top, these behaviors are rewarded. And slowly and gradually, repeating this task multiple times, the model will start to self-adapt and learn the good things. So this is a very basic definition of the self-adapting LLMs or SEAL, which this paper is talking about. If we actually dive deeper into the paper, this paper evaluates SEAL on 2 different applications. The first application is integrating new factual information into an LLM. So you can understand this as memorizing. And the other method is evaluating SEAL on few shot learning. So you can again understand this very easily by the notes example. For some kind of subjects where you have to actually just memorize, the notes you take are kind of different. You write down the important points which you have to remember so that you don't have to remember the whole textbook. Whereas for a subject like Maths, the notes will be different. You will not write down a lot of information to remember, but what you will do is write down any tricks, any formulas that you can apply, or maybe solving some questions, you have come up with your own formula, kind of a shortcut or something. You can note that. So what you're actually noting is a method to solve the problems and not memorizing. So these are two different kinds of applications. First one is more related to memorizing and taking notes about the important points. Second is finding tricks how to solve questions and things like that. So now let's talk about the first method that they were talking, knowledge incorporation. You can understand this with the first example that we talked about, taking notes for memorization. So how does this knowledge incorporation setup work? So you can look at this diagram. Again, you can see there is a large language model theta t. This is given a passage. You can see the title of this passage is Apollo program and there is lot of information about it. Here few lines are just mentioned, but you can see ... means there is more to it. So when it is given this whole context, it generates notes. You can see it has generated a self-edit or notes. Point 1, the Apollo program faced opposition from Kennedy's science advisor Jeremy Wisner. So this is the note that it has come up with. Now the same model, with the help of supervised fine-tuning, is trained on the notes that it has generated. You know, the self-edit. With the help of that, a new model is generated, theta t. Now you have to understand that this theta t has never seen this whole passage. It has only seen these notes. So that is where it slightly differs from the human example. Usually when we take notes, we have already seen the whole textbook because we have read the textbook and come up with the notes. So in our memory, we have the textbook as well and the notes as well. But in this example, in the SEAL example that we are talking about, the new model is only trained on the notes that has generated. It has never seen the original textbook or the original passage. So now this new model is asked the question. You can see, who was Kennedy's science advisor that opposed manned spacecraft flights? So you can look at this question. If the notes that were generated, the self-edits, if the self-edits or the notes have the answer to this question, only then the model will be able to give the correct answer. In this particular case, you can see the notes which it took were good and it had the information, faced opposition from Jeremy Wisner. So since it actually had this information in the notes, it was able to give the correct answer, as you can see. So this is how the knowledge incorporation setup works. And as you can correctly guess, the better the notes will be, the better the performance of the new model will be. So to understand that better, you can actually look at this example. You can see this is the input context or the passage, and based on this is the first iteration or first note that was generated. If you look at the notes, it's actually very small and it just has 2 points. And when this iteration 0, the model trained on this note was asked questions, you can see out of 3 questions it gets 2 of them wrong, simply because it doesn't have that much knowledge. It has not captured the whole essence of this passage. Next, if you move on to iteration 1, you can see this is slightly better than the previous one. We have more points, and when iteration 1 was tested over here, you can see iteration 1, there is some improvement, but it's not that visible. Again, we get 2 errors and 1 correct. But comparatively, we can see that the notes which were taken is slightly better. If we talk about the third iteration, iteration 2, in this you can see it consists of 10 points. So it has grasped a lot of information from this passage. And if you look at the performance of iteration 2, in all the 3 questions it gets it right, simply because it has taken better notes. So this is the knowledge incorporation setup, as I said. So with this, they actually did some tests to see how good is this method. So they actually took a model called Quen 2.57b, which is an open source model, and they asked factual content from the squared passages. So squared means Stanford's question and answering dataset. They took some passages from this dataset and asked questions on that. So they tested it against 5 different types of training. The first is base model, so it's no kind of training. As it is said, the pre-trained model is directly evaluated on the downstream question answer tasks, so no kind of training. Second is trained on the passage only. So this is very equivalent to the first point that we discussed, in the very beginning, where we talked about how large language models consume the data as is. So this is that kind of data, fine-tuning the model on the whole passage. The next method is training on the passage plus synthetic data. So this is very equivalent to how we humans work. So training on the passage is very equivalent to reading the textbook, and having synthetic data is taking the notes. As you can see, it is mentioned, this is the same setup as SEAL. So everything we talked about, taking notes in this manner and everything. So this is this method, but you have to understand a very big difference. We humans have years of learning. As we grow, our ability of taking notes also improves. Imagine a boy who is studying in 3rd or 2nd class. How would he take notes compared to a boy who is studying in 12th or 11th grade? The depth and understanding of how to take notes also improves, right? So similarly, this third method is like asking a very small child to to take notes. He doesn't know how to take notes. We are telling it to take the notes, generate the synthetic data, but it doesn't know how to take the notes. You see, it is mentioned without any prior reinforcement learning training. So just like the methods we discussed here, the model needs to take notes. That is nice, but it also needs to learn how to take notes. So when we look at this table, this is actually a single model that was trained in multiple iterations, and you can see its performance in iteration 0 compared to iteration 1 and compared to iteration 2. Its ability to take notes is improving. It is understanding that I have to generate more points and things like that. You can consider the model that was used in third point, trained on passage plus synthetic data, that can be very analogous to this one, iteration 0. So this is the third method. The fourth method is train on passage plus GPT 4.1 synthetic data. What does this mean? So this is very analogous to something like what we do with small kids. We tell the small kids to, read the whole textbook or read the whole chapter and learn it. After that, the teachers or the parents, they generate the synthetic data or notes for them. Since the models itself doesn't know to take notes, we can take example of very small kids. For them, parents, and in this particular case, a larger model like GPT 4.1, it generates the notes or the synthetic data. So this is the fourth method. And the fifth and the last one is the seal method. So it's not mentioned over here, but in this method, you just train on the synthetic data. So if you talk about the example that we are taking about a kid taking notes, so this can be very similar to a big boy who is actually, studying in 12th grade or studying in college. He's very intelligent and knows how to take notes. But the difference here is, as we actually talked about in the beginning, the new model that is trained, it doesn't have the knowledge about the context. So the seal method is very similar to, a student who has actually read the passage, taken the notes, but now many days have passed and the original knowledge that he had about the whole textbook, what he has memorized, all of that has vanished, and what he is remained with is the notes that it has taken. So that is the seal method. You know how to take the notes and you are very good at it, but that is all you have. You don't have the original text or original passage. So this is the 5 methods that they tested. In all these conditions, the model that was used is Qwen 2.57b. So what were the scores in this test? Let's have a look. So you can see this is the table. First is the base model, which has not been trained on the passage or any synthetic data or anything like that. It gets a score of 32.7. The next one, which is trained on the passage, or you can say fine-tuned on the passage, it scores slightly better, 33.5. The next one is trained on the passage with synthetic data or notes that it has generated. But this one is the model that doesn't know how to take notes. Even though it doesn't know how to take notes, but its performance does improve, scoring around 39.7. Next is the example of very small kid that we talked about. The model is trained on the passage and the notes for it is generated by GPT 4.1, which is a very big model compared to Qwen 2.57b. So since the notes were generated by a very big and smart model, so they were of course of very high quality and data. That is the reason the performance also sees a very big improvement, and we see 46.3. Finally is the seal method, and here you can see seal actually scores the best with a score of 47, and this is actually fascinating. But why so? Understand this fact. Observe this fourth method, train on passage and plus GPT 4.1 synthetic data. So what is this? This means Qwen 2.57 billion what was trained on the passage. So it has access to passage, it was trained on it, and then a very big model, that is GPT 4.1, generated notes for it. So you can consider these notes like the notes that are given by your tuition teacher. The printed notes that they give you. Those are very high quality data. So you have already read the textbook, you also have high quality data, and then you score 46.3. Whereas in the seal method, you don't get high quality notes from a very big model like GPT 4.1. And also you didn't see the passage as well. You just have very high quality notes that you have wrote yourself. Qwen 2.57 billion model. This Qwen 2.57 billion model wrote the notes for itself. And just with the help of those notes, it was able to beat the fourth method and score 47. Do you understand that? So this is like a friend of you who has read the whole textbook, goes to a tuition, and from that tuition he gets very high quality notes for that lesson, and then he comes to the test. And compared to you who may have read the passage but has completely forgotten it, and what you have is just the notes that you have generated, and still you were able to score more than him. And maybe that is why it is said that you should prepare your own notes, because even your friend got very high quality notes from the tuition teacher, but they were not the notes that he generated. So he can understand that notes up to some extent. Whereas the notes that you prepare for yourself will be very high quality, especially for you, because it is you who have generated it. and you will understand it fully. So that is the similar kind of thing we are seeing here in 4th and 5th condition. So this is the knowledge incorporation method that we talked about. As I said previously, two applications in the very beginning. First is integrating new factual information into an LLM. This was what we talked till now, knowledge incorporation. The second method is few shot learning. So the first one is kind of memorizing, how you can come up with such notes that it is of that quality that you don't have to actually see the passage again. That was one kind of learning and adaptation of large language models. The other one is very analogous to the example that we had, taking notes for maths, where you will not jot down points to remember. Instead, you will write tricks, any new formulas that you have developed for yourself and things like that. That is the few shot learning. Let's have a look at that. So what did they do in this few shot learning methodology? So they picked a very popular benchmark, that is the abstract and reasoning corpus, popularly known as the ARC-AGI benchmark. So as it is said, this benchmark is designed to test abstract reasoning and generalization from very limited examples. Each task includes a small set of input-output demonstration and a held out test input whose correct output must be predicted. So this is very similar to this interface. If you head over to ARC-AGI public dataset and copy that repo and run it, this is the interface that you will be seeing. You can see there are a lot of examples that are given so that you can understand what is going on. And with the help of that, you have to predict it. Let's actually try this one, So you see a shape like this and you can see it seems that this shape is kind of implemented one after the other. So you see, 3 at the bottom, 3 in the middle and 1 at the top. So okay, this is something we are able to understand. Maybe the direction is always towards the left. But now we come to the second example. Here we see that okay, the direction has actually changed. Now it's going downwards. So what could be the hint? One hint is, you can see this figure is pointing towards the left. And that is the reason the whole structure that has been formed is pointed towards the left, whereas this figure is pointed towards the downside, and as a result, the resulting formation is also towards the downside. Now if we closely look at this next example, here we see a filled square here and two filled square here, a pattern, and we see a similar pattern here, and also the direction seems to be upwards, and also you can see the movement is kind of upwards. Now let's look at this one. Similarly, same kind of pattern and also the movement seems to be towards this side. Then you have a pattern like this and you can see we have the pattern. But even then we can't solve the problem because there is some discrepancy. Here you can see, here we don't see any kind of voids in the middle. All these pieces are connected, whereas in the second one you can see all these three are disconnected. Talking about this one, here you can see again they are disconnected, whereas in this one all of them are connected, and then again in this one they are disconnected. So maybe we have to make some changes. One thing we can understand is this is a 3 by 3 square, and if you count this, it is a 9 by 9 square. So it could be that each of the squares is expanding into its 3 times. For example, let's have a look at this. So here we have a black, and have a look at here. We have a 3 by 3 square that is black. Here at the bottom again we have a black square, and here in the response example we again have a 3 by 3 square that is empty, whereas in this one it's actually filled. And just consider this 3 by 3 square. In this 3 by 3 square, since it is filled, we have this particular pattern mentioned over here. Similarly, in rest of the squares it is filled. In rest of the 3 by 3 grids that we have the filled pattern. Let's see if actually this theory holds on. If we move on to the second example, you can see in the center there is a black square and we have a 3 by 3 grid right at the center that is not filled. What about these two? Again we see two 3 by 3 squares that are not filled. Even in this side, similarly, we don't have two 3 by 3 squares not filled. Whereas in the corner one, we can see it is filled, so we have the pattern. The right side corner, it is filled, so we have the pattern. And at the bottom middle, we have it filled, so we have the pattern. Okay, so it holds on to in the second one as well. Similarly, in the third one, we can see the top three don't have the filling. That is the reason the top three grids, I think which is this one, they are not filled. These two are not filled, so the grids here also are not filled. The bottom one is not filled, so the bottom middle is also not filled. Whereas the corner left, the corner right and the middle right are filled. Similarly, we see this pattern true as well. Again, if we closely observe this, you can see this pattern holds true for this as well. Again, if we look at this, you can see we have a black space in L shape. Again, we have a black space in L shape if you count the grids. So this kind of pattern holds true. So now we know that the response grid will have 9 by 9 size. So we'll be applying some augmentation, that is changes to the grid that is already given to us. We will resize it to 9 by 9. That is done. Now we know the middle two will be not filled and one of the corners will be not filled. But the rest of the ones have to be filled with this pattern. So let's start filling. So based on the pattern, this is what we come up with. Let's hit submit and see. And you can see it says correct solution. So what did we do? We understood the examples that were given to us, and with the help of that, we tried to solve this puzzle. So as it is said in the RKG benchmark input and output demonstrations. So this is one input and output demonstration, input, output, and a held out test input and a held out test input, which is this one. We don't have an output for this. This is held out and we have to generate the output for this. So this is how the RKGA benchmark works. I explained it so that you actually understand the methodology that they used, and if you are one of my long time viewers, you know that we actually do test based on the RKGA public dataset. Similarly, how we are seeing here, the method that we imply in our testing is in context learning. I'll be telling you about this. If you head over to my channel, you can see there are various live streams which have the ARC prize as mentioned. So we do this testing. We also compete models and do a battle of chess between them. And there are of course various other videos in my channel. So if you're liking the content up until now, please do hit the like button and subscribe to my channel. Let's head back to our topic. So we were talking about the few shot learning methodology, and I just explained you about abstract reasoning corpus. How does it work? So you might recall in the previous method, that is knowledge incorporation setup, the model used to take notes in the form of points, and just as we digest the whole context into few points, the similar method was implied in the knowledge incorporation setup. But I said the few shot learning method will be different, because just like how you note down tricks or any learnings that you have come up with in a subject like max, in the same way we do it in the few shot learning methodology. So how does the model actually learn in this method? That is the few shot learning method. So in this method, actually the model is given some tools, and with the help of that, it does some data augmentations like rotations, flips, reflection, transposition, resizing operations like changing the grid resolution, things like that, and optimization parameters, learning rate, number of training epochs, and all of that. I'll explain you what is this. So data augmentations. When we were solving this question, in our mind, we actually tried to, flip these grids, tried to see its reflection. We resize the grid, based on what we are able to see. We were able to come to the conclusion that yes, we need a 9x9 grid instead of a 3x3. So in our mind, we did all those rotations, flips and everything, so that when the model is able to do it, we are giving it the tools to do data augmentation. That is, change the data that is given to it, rotate it, flip it, see reflections, transpositions and things like that. Also you can see it is said example changing the grid resolution. So that is one thing that it can do, or it can specify in its notes. The next thing is optimization parameters. So this can be a bit complex because it is something related to how the LLMs are trained, the number of epochs it goes through, or the learning rate. So this is the core information, how you will train your model. So learning rate and epochs, it is something that is very core to, training neural nets, and things like LSTM, a convoluted LSTM, transformers for that matter. To make you understand in simple terms, learning rate is the speed at which it actually goes through the data. It could be analogous to you reading a textbook. At what speed are you reading? So if you go through it very fast, you just read it in very fast pace, and you might not learn a lot. But similarly, if you learn very slowly, that will be very exhausting and very tiring for you, and it might not be optimal. So there has to be a sweet spot of speed that you go through the textbook. So that could be very similar to the learning rate in models. How fast does it go through the data? Next is epochs. So epochs is how many times it goes through the data. And this is very similar to the human example that we are talking about, how many times you are reading your textbook. The more times you read it, the more familiar you get with it. Even there has to be a limit. If you repeat it multiple times, it will be exhausting, and if you repeat for very few times, maybe just one time, you might not remember it. So there is a sweet spot of learning rate and how many epochs a model is trained for. So these are the two things that are the nodes in this particular method, that is few shot learning method. That is the data augmentation, how the data should be augmented. The second is optimization parameters. At what parameter should the model be trained? To more understand this, let's get back to this example. Again, we have the LM theta t, the model, as we talked about previously. And if you look at few short examples, you can see this is very similar to the interface that we just talked about, this particular interface. Input output example, input output. Here again, input output, as you can see. And if you closely look at the pattern, you are clearly able to see 3 boxes are filled, the colors are changed, and the same boxes are filled. Here you can see these 3 boxes are filled and the same pattern with different color, and even in the third one, same pattern, different color. So this is the pattern that the model has to understand. So when this is fed into the model is not giving us the response. Here the model is not asked to give us the response. Instead it has to give us the learning from it, or whatever notes it has understood. So just imagine looking at this. What notes could you come up with? One thing you can see is we are changing the color. So there is color augmentation. We have to change the color. Okay. Are we changing any sizes? No, because this is a 3x3 grid. This is a 3x3 grid. Are we doing any kind of rotation? They are in the same rotation and there is no changes in that. Is there any need for rotation augmentation? No. Is there any kind of repetition? Just how we see here, there is actually a repetition. You can see there are multiple times it is coming. Where here, we don't see any kind of repetition. It's just the same thing, but with a different color. So this is something that we can understand. Okay, whenever a question like this comes, there is no size augmentation, rotation augmentation, or repetition augmentation, or any kind of chain augmentation. The patterns just following one after the other in a chain. There is nothing like that. There is just one basic augmentation, which is color augmentation. So this is the same thing which the model does. It makes the self edits, the notes. It says, is there a basic augmentation? You can understand this as color augmentation. It says true. There is a basic augmentation. Is there any size augmentation? No. Chain augmentation? No. Repeat augmentation? No. So this is one of the learnings that it has generated, and you can see how this kind of learning is different from this kind of learning where we actually kind of jotted down the notes. This was more about retention of the data, and this one is more about understanding the patterns in the data. That is the reason I said this is very analogous to max. Finding tricks. These are actually tricks that you are finding out. So this is one part of the notes or the self edits. The other part, the model actually also tells when you are actually training a model on these tricks or notes, have this learning rate or this number of epochs. So that is noted, and based on that, a model is trained. And you can see this is the new model, theta-t. Now this model is asked the question. You can see this is the question. But similarly in the previous example, in this example, this new model has never seen the actual passage. Very similar to that, this new model has never seen these examples, but still it comes up with the correct answer because it knows the pattern. It has been trained on this pattern, so it knows that okay, whenever I see something like this is most likely the answer. So this is the another kind of learning that we are talking about. So imagine this kind of methodology is actually implied on the ARC-AGI benchmark, and the model slowly and gradually starts learning how to solve these types of questions. This is very similar to a max class. Generally in a theory-based class, there is some explanation, but most of it is about memorizing things. Whereas in a max class, your teacher or your tuition teacher or anyone, he will be telling the formula in the first 5 minutes, I guess, for the class. But the rest of the class, you practice problems on that question. Why do you do that? So that you develop internal patterns and these kind of augmentations and self edits in your brain. That is the same thing that has been talked over here. That is the reason I told you the example of take notes differently in a theory class and you take notes differently in a max class. So this was the method, the few shot learning method. Let's get into the results. So how did they test it? They picked up a model that is Llama 3.2 1 billion instruct. Can you imagine? This is a 1 billion model, a very, very small model. And they have said that this open source model doesn't have any kind of ARC specific pre-training. So it has not been trained on the ARC-AGI dataset. So it's not possible that it already knows the answers and everything. So in the rest of the method, they have told that they have curated a subset of 11 tasks from the ARC training and 8 from the ARC evaluation set. So a few number of questions they have selected. Instead of doing a test on the whole dataset, they've selected a few number of questions and they applied this kind of methodology, that is the SEAL method. So in our previous method, we saw 5 different cases, right? Base model, trained on passage plus synthetic data, and I think all of this explanation was done previously. So that was in the knowledge incorporation method. So what are we comparing against in this method? So first method is in context learning. I've already told about this. In context learning is just chatting. What do I mean by that? For example, whenever I actually send models this question, I send them using the in context learning method. I have a copy task prompt button. So let me actually copy this, and what I'll do is I'll open Chatgpt and I'll show you what do I send and what do I mean by in context learning. This is the whole prompt. Here you can see I am giving it the example input in the form of grids. This is the example input. This is the output. Input, output. Input, output. So these kind of 5 examples I have given to it, and then I give it the last test input. With the help of this, it has to predict the output. Now you can see it is coming up with the response. So this is in context learning. I have given it all the information within the context, and it has come up with the response. So it could be in a single response or in multiple responses. Like I will be giving you one example, have a look at that, then I'll tell, now I'll be giving you second example, have a look at that, third, fourth, fifth. Now I'll give you a test input, this one, predict the output. So you could use multiple chats or a single chat, but this is what is mentioned over here in context learning. See, it is mentioned Llama 3.2 1 billion instruct is prompted with given few short examples and directly queried on the test input. The next is TTT plus self-edit without prior RL. So this TTT means test time training. So what is test time training is, it is mentioned over here. By the way, you can have a read at it, and I will be actually pasting this link of this paper in the description, so you can actually have a read by yourself. So test time training by many is considered to be the next paradigm. So we already have pre-trained models, that is GPT-4 and all those pre-training models that I told you about before. The next models are reasoning models. OpenAI O1, O3, Gemini 2.5 Pro. These are test time compute models. These models use more compute. They think and come up with a response. Similarly, like the reasoning models, that is OpenAI O3 and the ones I told you. The next paradigm is test time training. These models, while they are having a conversation, as the conversation goes on, they temporarily adapt their model weights. You can simply understand they temporarily adapt themselves based on the input the model receives. So we are very close to test time training kind of neural nets. Whenever we have a conversation, whenever we do anything, our internal neural structures and model weights changes. So you can look up about test time training in the internet or have a conversation with Chatgpt or Gemini 2.5 Pro. I clearly say anyone who is my subscriber, use Gemini 2.5 Pro until it's free. Yeah, having said that, you can have a conversation with that model to understand what is test time training. So the second methodology is test time training with self-edits without prior RL. So without taking much time in this particular method, as I already mentioned you, right, previously in knowledge incorporation, the third method, training on passage plus synthetic data, but without RL training. This was very similar to a person takes notes, but it's a small kid. I give you an example of how the quality of notes changes based on which class you are. If you are in 12th grade, your quality of notes will be very good. If you are a very small kid like in 3rd or 2nd grade, your quality of notes will be very bad. So the third one was that, generating synthetic data but not knowing how to generate a very good synthetic data. So this is similar to this method, test time training with self-edit without prior reinforcement learning. Without prior learning of how to actually come up with self-edits or notes. And the third one is Oracle test time training. So this is the optimal condition based on human crafted configuration. You can consider this as ideal conditions. What is the maximum limit the model could have done? So these are the three methods, and the fourth method is obviously the seal method. As it is mentioned, there is no kind of training and there is only self-edits. Just like how we talked in this. All these were trained on the passage, but the seal method was not trained on the passage, but it just had the notes. So similarly here as well, it will just have the notes. If I tell you in this example, it can be very analogous to, saying that all these methods had access to this data, this training data or example data. Either they have read it or they have been trained on it. That is test time training, all these three methods. Whereas the seal method doesn't have access to this, it just has access to this. What were the results? So in context learning, so this is similar to this example that I showed you. So in context learning, it scored as 0, and it was pretty much obvious because it is a 1 billion model, Llama 3.21b. So solving questions like RKGI is kind of difficult, so it gets a 0. But when it went to test time training and also generated some notes of understanding, as I explained over here, using this methodology. But it was not pre-trained on how to take good notes. It was instructed to take the notes, but it is like saying a very small kid to take notes. So that is this method, without prior RL. The scores do improve because of test time training. The success rate goes to 20%. Next is the seal method. The seal scores 72.5%. And we have to remember, in the seal methodology, it doesn't get access to all of this, but still it was able to solve. It gets 72.5%, a 1 billion model, even able to solve any question in the RKGI dataset is impressive to me. And Oracle test time training is like the ideal benchmark, so the success rate is 100. So now you see, even in this kind of settings, the seal method does perform very good. So these were the two conditions that is mentioned in this paper, self-adapting language models. But there are some limitations as well that they have mentioned in this paper. So here you can see limitations. Catastrophic forgetting. So this is very similar to, again, I would like to come to the human student example. Whenever you're taking notes or you're revising a note, you will read one paper and after that another paper, or after that another paper. So like this you have gone through 5 papers. So when you are in the 5th paper that you have just read, you will have that in your memory and you will be very thorough with it. But the first paper that you read, you might have actually forgot something from it. That is the same behavior or kind of a limitation that is seen here, catastrophic forgetting. That can be very visibly seen in this kind of chart. So it can be a bit complex at the very beginning. So this is the self-edit iteration 1, 2, 3, 4, 5, 6, 7, 8. So here you can see first it learns a thing. So this thing has a score of 0.38. After that it learns 2 things, 1, 2. So you can see since it just learned the second thing, the learning is very nice, but it has actually forgot some of the previous one. The first thing that it remembered, or you can see the first question that it remembered, from 0.38 it went to 0.36, a slight degradation. Then it learned the third question. You can see the performance is good, but again the first question it has forgot something. Now in the 4th iteration you can see the performance has degraded, and slowly and gradually by the end of 8th iteration you can see the performance has degraded quite a lot. So this is catastrophic forgetting, and this is one of the limitations that they have mentioned in this page. See, you can see they have mentioned, can the model adapt to new information repeatedly while preserving prior knowledge? So the answer is yes, but the quality of that retention does go down. That is what it is mentioned, catastrophic forgetting. So there are more limitations mentioned over here, that is computation overhead and other things. I will be linking down the paper so you can have a thorough look of whatever is mentioned in SEAL, that is self-adapting language models. So how did you like my explanation? I hope you like my rambling and I was able to make some sense of what was mentioned in this paper. If you liked the video, please do hit the like button, subscribe to my channel, and please tell me in the comments if you would like more videos like this that explains the latest advancements in AI. I will be very open to your feedback. With that being said, I'll catch you guys in the next one.